Recovery of steam and sensible heat in spray dryers and industrial dryers. General objective: introducing innovative and efficient methods for water and steam recovery. Challenges in industries, especially in spray dryers for ceramic tiles, pharmaceuticals, and chemicals. Introduction to the integration of traditional and modern systems. Architectural inspiration: wind catchers and domed roofs. Traditional wind catchers capture and direct fresh air into interior channels. Hot, pressurized air rises through the central shaft. Fresh incoming air is deflected toward mudbrick walls. Moisture condenses slightly, keeping walls damp. Result: cooled and moistened airflow for desert climate. Domed roofs provide structural stability against heat and pressure, reduce solar load and regulate thermal conditions. Curved geometry directs internal airflow toward wind catcher channels. Our steam recovery system, steam flow, follows similar aerodynamic principles. Core hot flow rises centrally, like wind catcher shaft. Peripheral moist steam guided to walls and collectors. Dome-like geometry inspires separation and condensation zones. Outcome: efficient steam recovery and energy saving. Slide title: Steam Heat Separation Zone. Inspired by traditional Iranian architecture. Content: the steam separation zone efficiently separates and collects steam and dry heat from the spray dryer. Steam enters the upward converging chamber and passes through perforated diffusers and grid-like separators, which capture fine particles, direct steam toward peripheral collectors, reduce central turbulence. This design conceptually resembles traditional Iranian domes and wind catchers, which naturally channel airflow and heat. Conical perforations in diffusers mimic ventilation openings, ensuring optimal distribution and maximizing energy recovery. Key benefits: efficient steam and heat separation, reduced energy loss. Architectural inspiration enhances natural flow control. Integration of traditional domed architecture with modern systems. In traditional hot, arid climates, domed ceilings with converging walls naturally directed heat toward the center, where it was expelled through a central vent. This design maximized air circulation and passive cooling. By integrating this architectural style with modern energy recovery systems, we can leverage natural airflow patterns for optimal heat management and energy efficiency. The central venting concept complements steam and heat recovery systems, enhancing the environmental performance of industrial processes like spray drying. Furthermore, this system can efficiently separate steam, dry heat without energy consumption or moving parts, much like the traditional domed architecture. It directs high-pressure dry heat towards the center while guiding steam and moisture to the walls and surrounding collectors, making it ideal for condensation processes. Electricity generation from waste heat with heat pump systems. Industrial furnaces, kilns, and spray dryers release substantial amounts of secondary waste heat that is often lost to the environment. Unlike conventional CHP systems, which primarily recover heat from generators to produce both electricity and thermal energy, this approach specifically targets the exhaust heat from kilns, spray dryers, and other high-temperature processes. By integrating heat pumps, organic Rankine cycle (ORC), or Stirling-based systems, this otherwise wasted thermal energy can be converted into electricity, further increasing overall efficiency. For example, a large-scale facility such as Mohawk could generate 3 to 5 megawatts of electricity from its process waste heat, enough to offset a significant portion of its energy demand while reducing greenhouse gas emissions. Steam plays a central role in this process. It serves as the working medium for power generation, and after producing electricity, the steam can still be recovered, condensed, and reused as clean water or for industrial purposes. Key benefit: cleaner electricity production beyond CHP, optimized use of furnace and dryer exhaust heat, reduced fuel consumption, significant water savings, and improved sustainability in large industrial operations. Key challenges in steam and water management in spray dryers. Each of these challenges includes several sub-challenges, with examples as follows: presence of dry heat and contaminated vapors. In food, pharmaceutical, and chemical spray dryers, vapors contain sticky or acidic/alkaline particles, making active steam separation difficult. Very fine and sticky suspended particles. Food and pharmaceutical industries. formation of sticky layers on separator surfaces and pipes, mineral industries, silica and oxide particles causing erosion and clogging. Variation in the nature of pollutants across industries, chemical industry, alkaline and corrosive vapors, food spray dryers, acidic and organic vapors, metal industries, water vapor mixed with oil and metal oxides. High velocity of exhaust gases in spray dryers causes contaminated steam and particles to bypass conventional separators, high water consumption and environmental impact. Large evaporation volumes require sustainable water management and prevention of wastewater pollution. Major challenges in acidic and nitrogen-based spray dryers: severe corrosion, acidic vapors and nitrogen oxides accelerate corrosion of metal surfaces, requiring costly resistant materials, e.g., high-grade alloys, coatings. Formation of sticky and aggressive deposits, acidic aerosols and nitrogen salts create hard, adherent layers on chamber walls and pipes, leading to frequent cleaning shutdowns. Health and safety risks: release of acidic mists and nitrogen oxides poses serious risks to workers' health and requires advanced gas scrubbing and monitoring systems. Environmental concerns: emissions of acid gases, HCl, H2SO4 mist, and nitrogen oxides, NOx, contribute to acid rain and air pollution, demanding strict emission control. Operational inefficiency: fouling, corrosion, and erosion reduce dryer efficiency, increase maintenance frequency, and raise operating costs. Research and development in specialized spray systems: initial tests on electrostatic systems for capturing fine particles in nitrogen and acidic environments, development of specialized separators for submicron particles. Investigation of voltage/frequency variation on system performance, testing steam scrubbers to remove natural gas combustion particles and other pollutants. Ongoing research steps: development of precondensers for separating organic/inorganic content, pilot development for nitrogen and acidic vapor sprays. Step-by-step description of our advanced steam and heat recovery system. Our developed steam and heat recovery system for spray dryers consists of 5 main zones that efficiently recover steam and heat across various spray dryer designs. Zone 0, Particle Separation Zone. This zone is designed to separate suspended particles from the exhaust gases of the spray dryers. Based on the type and quantity of particles in the spray dryer output, which are determined by production specifics, an initial separator is installed to remove large particles. Generally, spray dryers do not contain particulate matter but primarily carry acidic vapors and nitrogen. This zone may include one or more components. Electrostatic precipitator, dry or wet scrubbers, filtration systems, special electrostatic system for acid vapor separation, currently under development. Zone 1, Dry heat and active steam separation zone. This zone is specifically designed to separate dry heat and active steam. For ceramic tile spray dryers and similar applications, this separation includes 4 parts: central high-pressure dry heat separation, using a pedal-shaped inlet design. Additional dry heat is separated and purified for reuse. Converging diverging cones. These cones, inspired by traditional domed ceiling designs, efficiently separate heat from steam. Steam recovery. The final part of this zone recovers latent heat from steam for further use. This zone includes smart control systems, bypass valves, and cleaning vents. The controller ensures minimal impact on spray dryer operation while optimizing energy consumption, activating fans and components only when necessary. Inlet vents adjust for cold air in summer and warm air in winter to maintain central heat balance, assisting steam flow toward the walls and enabling more efficient recovery of lye. Zone 2, Latent heat recovery and final cleaning. This zone is focused on recovering the latent heat from steam for use in heat pumps and other applications. It also performs final cleaning of steam from suspended particles and combustion residues from natural gas. The recovered latent heat contributes to energy efficiency and enhances the system's overall performance. Zone 3, Condensation Zone. This zone marks the beginning of condensation, utilizing turbulent nanotube composite plates and carbon nanotubes for efficient condensation. The condensation process is aided by Stirling engines and high-pressure pumps for large-scale applications such as power plant steam recovery, which has been tested in pilot phases. Turbulence plates and carbon nanotubes. Turbulence plates, separation of latent heat from steam, reduced energy consumption by utilizing latent heat. Carbon nanotubes, direct condensation of steam into water without energy consumption. Significant reduction in refrigeration load and energy consumption. By integrating advanced steam and heat recovery technologies into the SACME ATM 110 spray dryer system, the final refrigeration load can be drastically reduced. As shown in the chart, the energy demand decreases from 4,700 tons of refrigeration, 16,520 kilowatts, to less than 50 tons, 176 kilowatts, achieving an overall reduction of nearly 99%. This demonstrates the system's ability to maximize heat and steam recovery while minimizing energy consumption, without affecting the dryer's operation. Final condensation and heat pump integration. Steam condensation. Active steam passes through CNTs and is converted into clean water. Heat pump utilizes energy recovered from spray dryers and roller kilns for cooling and condensation. Upgraded heat pump. Our advanced design replaces Monel with a lower-cost substitute material. Carbon nanotubes, CNTs, are grown on this new substrate, providing a higher thermal conductivity, which reduces both energy and water consumption by up to 30%. Heat pump system and cooling for condensation. Specialized heat pumps designed for efficient energy recovery. Significant reduction in energy demand for condensation cooling. Large-scale water and energy-intensive industries, e.g., refineries, power plants, consume vast amounts of water. Through the sustainable development of advanced heat pumps and the use of Stirling engines, substantial amounts of clean water can be recovered. According to the laws of thermodynamics, condensing 1 ton of steam requires the evaporation of nearly 1 ton of cooling water in an evaporative tower. When losses such as blowdown and drift are included, the total makeup water demand typically rises to about 1.1 to 1.5 tons of water per 1 ton of condensed steam. By integrating energy-free condensation systems and next-generation heat pumps, water consumption can be reduced by more than 70%, while producing clean, standard-quality water and optimizing energy use. Recovery pool. Collection of clean and safe water in dedicated recovery pools. Environmental challenges of spray dryers. Spray dryers across various industries release significant amounts of pollutants and fine particles into the atmosphere. Slurry particles, sometimes smaller than 1 micron, can be harmful to plants and ecosystems. Chemical and pharmaceutical spray dryers emit high levels of acidic vapors and toxic gases, which pose serious environmental and health risks. Key challenges include resistance to acidic vapors, nitrogen-based emissions, and managing ultrafine particulate matter. Solutions and pilot developments. Advanced steam scrubbers and electrostatic separation systems are being optimized to capture fine particles and gaseous pollutants. The system can prevent the release of over 90% of acidic and toxic vapors, significantly reducing air contamination. By utilizing recovered energy, fuel demand is reduced, leading to lower greenhouse gas emissions and improved sustainability. Ongoing pilot projects and simulation studies are supporting continuous improvement and scalability.